Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Eleni Stark and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is radio protocols in theory and practice. Our speaker today is our support engineer, Manfred Schormatz. He will hold today's webinar and also answer your questions. In addition, our software engineer, Matthias Hause, accompanies us today. He's our technical expert in the background and will have a look at your questions during the webinar and support us in answering them. Before we start the webinar, I would like to point out one thing. You'll be muted during this webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via our chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. Chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.de. We will try to answer all the questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email several days after the webinar. You can also watch the recording of today's webinar a few days later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I will hand over to our speaker Manfred Schormatz and I wish you an exciting webinar.
Yes, good afternoon, ladies and gentlemen, participants to the webinar this afternoon with the topic Radio Protocols in Theory and Practice. Once again, thank you very much, Eleni, for the introduction, and also welcome to Matthias, sitting on my right-hand side here, who will be looking and attending to your questions. Right, we have an interesting topic which is very wide, radio protocols in theory and practice. What do we talk about? I have a brief overview here with a short introduction of protocols. Protocols obviously are bound to software as well as hardware. And we have the topic of the physical layer. We have something on antenna types, range and attenuation. Then we'll go into our radio modules a little bit and also the engineering tools we have available with a short summary. Right, let's kick off with the first one here, Introduction to Communication Protocols. Now, I tried to find a suitable sentence to summarize all of this. A communication protocol consists of a set of rules that allow two or more entities to communicate information via a physical quantity. And then we have, this defines the rules, syntax, semantics, and synchronization of communication, as well as possible error recovery methods. In other words, protocols may be implemented by hardware and software. Right, I highlighted some points here, which we'll discuss in detail. At the bottom, you'll see our little pictogram here. The green little squares or rectangles could represent our radio modules. In effect, what we'd like to do is convert some digital data into an RF signal, transmit this and receive it and convert it back to a digital signal. That's what it's about. Let's kick off and start off with the introduction. I have here a little bit on the software, because I mentioned hardware and software are both equally important. On the right-hand side, you'll see something which looks like the 7-layer protocol of the so-called OSI-model, or the Open Systems Interconnection Reference Module. This is what it's all based about, and the OSI-model tends or aims to keep the different levels of software compatible to different systems. In effect, what we do, we condense some of these levels a little bit to what we have in the middle here at the bottom, the media, which is basically then the physical, the data link network, sort of the media layers, the hardware. Then comes a layer which we call transport, and above that the application, which is in basically application, presentation, and the session out of the ISO 7 layer model. The protocol stack is an implementation of a computer networking protocol suite. So we have different suites or layers which combine to form this protocol which we'd like to use. Let's go and dig in. The radio protocol in practice. Now, if I want to send any message via radio, I have to stick to certain rules. And obviously, other than to a wired link, I need to prepare this receiver for a package to be transmitted. And in doing that, I have a preamble, which aims to get the signal going. The receiver will recognize there's something on the air. In other words, a form of synchronization, a message start indicator. Right, then I have a few more bytes consisting or comprising the header. It is still marked gray, a little bit more on that on the next slide. Then obviously the payload, the actual information I'd like to transmit. In this case, typically hello world or whatever your payload might be. And then I round this off with a checksum and an end of the package indication. Let's dig in. The next one, the radio protocol in practice is, just before the payload, and the header part here is very important because that tells our radio package what it's all about. These are the rules we define. So the header content here comprises, amongst other, the addressing formalities. So where from, where to does my message need to go to? It allows direct addressing and also defines networking topologies, which could be typically a star or peer-to-peer or whatever other topology you have. So the addressing rules set up here. There are different levels of addressing you could apply as well. Apart from that, there's a bit more here. The routing information, if we have a system whereby we actually like to pass on a message or a multi-hop system, we need some routing information, basically also comprising the source as well as destination address. This allows for routing or mesh networks. Then there's an element here, time to live or TTL, as well as hop counter information. If I have some of the mesh system, I cannot keep this message alive forever. Somewhere it needs to end. And by using a time to live and a hop counter method, I rule or control this. In other words, here I have the option used, which can be used for flooding or routing mesh topologies. Maybe a little bit more about that at the later slide. Let's look one further. Also in the header content, as I address, is my fragmentation information. If my package is fairly long, I could actually break it up into smaller packages. If I have higher payloads, I could have acknowledgement information in here, which allows retries for assured data transmission. It verifies my data transmission. And also the possibility of data encryption, which is becoming more and more important nowadays. All right, let's dig in and see what else. I have a slide here trying to place our sort of proprietary protocol somewhere in this big screen of radio standards. Invariably, with any radio standard, I like a big, large range, and I like a lot of data to get through. So data rate versus range are always critical aspects which you need to consider. And obviously, there are physical limitations. On the higher range, we have the mobile RF. On the higher data rate, typically Wi-Fi. At the left bottom here, for the personal area networks and the local area networks, we have the typical Bluetooth, Thread, NFC, and others like Ocean, Homematic, KNF, and so on. We try to fit in between there with our proprietary to actually obtain the best data rate for whatever overhead we have. Just as an indication, obviously there's a bit of hardware which we need as well. Now the next slide already brings me into the theory. To get all of the data across the radio, in other words, the binary data consisting of zeros and ones, I need to modulate this onto a carrier signal, because an electromagnetic signal can only be created or generated around a high frequency signal, which is my carrier signal, and modulated onto that, I'd get a RF signal, which then contains the information. You see this in the left-hand top here. And the right-hand side, we see here, this is our implementation of a so-called frequency shift keying implementation. The carrier frequency would be the center frequency, which we would have in the middle here, right in the middle. Could be our 868 megahertz or 2.4 gigahertz or whatever frequency around there. And if I have 2 FSK, my information, the binary data, would take place by shifting this to the left and right around the center. But obviously I need to stick to rules. I cannot put endless amount of power into the system. I need to stick to band limits and channel limits. So these are the rules and regulations I need to comply to if I want to use a certain frequency. On the right-hand top, once again, a little screenshot of one of our oscilloscopes here, where you can clearly see the frequency shift keying around the center frequency of 868 megahertz in this case. Right, there's a lot of theory. I'm going to carry on and see how can I get these ones and zeros across this channel. And in effect, there are some niceties which we make use of as well on the physical layer, which we call the direct sequence spread spectrum, or DSSS. This is a digital modulation scheme allowing to achieve higher ranges. We spread this before sending the actual data. So if you look on the left-hand bottom, the 1010, which we have here, after coding, according to a certain pattern, I'd get 4 ones and 4 zeros and 4 ones respectively. So I have a certain redundancy in my data going across the ether. And then at the other end, obviously, I need to take care of it in the reverse direction. So the transmitted data here is a redundancy of ones and zeros for my input. Let's have a look and see what happens at the receiving end. Here's a new terminology, FEC, forward error correction. Erroneous bits of the received data are corrected. Now this is statistical correction. If out of my 4 bits of ones which I receive, which I have here, there happens to be one little error, a 0, I can still correct it because the majority wins. And the same goes for the 4 zeros. This should be a 0. I can correct that as well. And I end up with my correct data here. So forward error correction, a method which improves my data sensitivity and reliability at the receiving end. 2 little terms, DSSS and FEC. Let's have a look at the next topic, which I have here, antenna basics. Now this is very, very important because only through a good antenna can I get my stream of ones and zeros into the free space or ether, and the better the antenna, the better my results. Right, what do I need for a good antenna? I need a antenna which delivers maximum power, and this only occurs with a so-called resonant frequency. In other words, if you look in the middle here, my maximum power delivered at a quarter wavelength, and a quarter wavelength obviously would be the top half of this antenna. That would be my radiator, a copper or aluminium wire, and the reverse part thereof, the negative or the ground or a ground plane. Now, if I have a resonating antenna on 868, I'd have a voltage maximum at the peak of the antenna and a minimum of current, in other words, the maximum reflection and the minimum of loss. I could imply or apply this on a PCB as well and use the ground of the PCB as the ground plane. That would be a monopole antenna using the ground plane, and we would talk of an effective quarter wave antenna. What I have on the right-hand side here is a pattern or an emission pattern of this typical dipole antenna. Now, a wire antenna, as we know it classically, would radiate in all directions, lovely as you'd see it on the right-hand side here, a little bit less towards the top end and the bottom end. We could affect or influence this by putting reflectors or radiators onto an antenna. We talk of a gain then. This would actually strengthen the signal in a direction, but in practice not really amplify it. It would gain or strengthen in a direction, and the same would hold for a receiving antenna. Right, a bit of theory and resonant frequency I need, and the quarter wave. A last little topic here, for 868 megahertz, the length of this antenna here would be about 8.3 centimeters, which is calculated by the well-known formula of C, which is constant speed of light or radio frequency, being equal to the wavelength lambda times frequency. Now, if I want my lambda, the length here, I divide C, 300,000 kilometers per second through a frequency of 868, I should end up roughly with 34 centimeters. A quarter wave would then be 8.4 centimeters. Right, a bit of theory. Let's go on to the next slide. And if you look at all of these typical antenna applications, in the middle, the PCB antenna, which I have here, is a helical type antenna directly on our PCB. And if you would straighten this out, you would theoretically or practically get an antenna length of about 8 point something centimeters. In other words, a quarter wave antenna for 868 megahertz. The left-hand side here is a typical chip antenna. What we have inside the chip antenna is a helical winding of copper wire or transmission wire. The nicety is that I can simply solder it in without much effort. It costs a little bit more. And then a bit more on the expensive side is then the dipole antenna or a stub antenna, which I can use externally and connect it via coax cable. Right, a lot of theory on antennas. I'm going to leave it at this here. There's one more slide which I'd like to point out. On my whole transmission path, I always have to start off with the transmitter. In this case here on the right-hand side, the TX power, and I have a certain power level, mostly about 14 dBm or sometimes 27 dBm on 868, depending what you are applying. Then already we have some loss on the antenna itself. Then the red line indicates my radiation losses through free space. The receiving antenna in itself also has some losses, and what I'm left with is a margin of signal, which is my useful information, which I can work with. If I have a too small margin, I end up with noise only, and my signal is now more usable. Now, in order to get a maximum and ideal signal across, very important is my antenna height, which I see on the right-hand side here, the transmitting antenna and the receiving antenna. And we have here a so-called ground reflection model. Not only the ground, but other buildings, environments, and obstructions in the vicinity could influence your distance of transmission. There's a lot of theory you could read about. Two little points I'd like to just point out on a mathematical level here. There are many prediction programs and algorithms which you can use to calculate the distance of an antenna. Now, in essence, if you look at the bottom one, the so-called free space path loss, in effect, don't go into this formula, but what is important here is the frequency, the F, taking place in the calculation, and also considered is the radiation in a spherical direction in all directions. Now, what I have here, the bottom two, the blue and the red lines, I'd like to indicate that I have a certain loss or negative gain, depending on frequency, first of all. But the theory here is not really what we experience in practice. Now, what happens more often is a so-called, or what we could apply more often is a so-called two-ray ground reflection model, which seems to be more realistic. And this model actually makes use of two parameters, the H of the antenna and the H of the receiver, height of the antenna and or transmitter and receiver. And that is roughly what we have in the top here, that 2R model of 1.5 meters above ground. And here you can see that with our modern modules ending somewhere here at 120 dBm gives us roughly 2 kilometers, provided we have a clear Fresnel zone, open space around, and not too many obstructions. So physics is a limitation. One more bit of theory slide which I have here. What is my link budget? Is the amount of information I end up with after having received a signal. And that is comprised of my actual transmitted power minus the sensing on the receiver side in dBm. And here I have 3 graphs trying to highlight the height of an antenna and the critical influence of antenna height. You can see the bottom one, antenna height of 1 meter above ground. Your distance will reduce drastically, and we have the estimated range on the left-hand side. Now, with a height of 6 meters, which is a gray line here, you can see already that we can reach well above 4 kilometers with our Triton module, and with our Tarbos 3, we could actually reach somewhere about 10 kilometers. And there are other methods, means of actually improving on this. But keep in mind, the height of the antenna is very critical, somewhat critical as well, the frequency. I think this is enough of radio theory. Let's actually dig into the next slide here. I've put in some basic information here. Very often I've been asked what's the difference between dBm and watt. The one is a logarithmic calculation of watt, and what you'll see here is that the little scale here, I've put in 4 values. 14 dBm is equal to roughly of 25 milliwatt. And if I go up to 27 dBm, 500 milliwatt. Now, these happen to be the 2 sort of limits which I have on the 868 megahertz frequency, which we use very often, depending on which of the bands, either the one or the other. On the right-hand side, factors influencing my distance and output. Just as a quick summary, is obviously the gain sensitivity, body and body effects, and so on of the antenna. The output power obviously plays a role, but we are limited by law. Affecting us could be radio pollution, and we talk of selectivity and blocking. And very important in the actual environment. Normally we want to have a good line of sight, LOS, which I have here. Obstructions are a bad influence. Reflections and multipath fading are all elements of influencing my range. Then a last little topic here, coding methods. Depending on how I code, I will obviously improve my distance. You could use Manchester coding. We had FEC and DSSS. Have a look at those. But out of interest, I have on the left-hand bottom here a little rule of thumb. A gain of plus 6 dB is about twice the distance. If I double frequency, the transmitting frequency are roughly half the range. That's a rule of thumb. If I have plus 3 dB gain, I double the power, and for about plus 10 dB, 10 times the power. Now, just out of interest, apply these little rules to my 14 dBm. If I add 3 dBm to 14 and end up with 17, I double the power, becomes 50 milliwatts. And applying the last rule, 17 plus 10 to 27, 10 times 50 gives me 500 milliwatt. Right, so my rule actually does work. little exercise. Let's carry on the next one here. What does all of this mean in practice? Antenna types determine factors such as gain, range, radiation characteristics. Test procedures are critical at the end of the day. If I want to apply a certain antenna, test on site, and very often we do it by trial and error in the respective environment. Now, the bottom pictogram here, all I wanted to show there is how diverse our radio environment could be, from industrial to domestic to open space. The options are manifold. I'm going to leave it at that. One more slide here on the radio module, which we then actually imply. And what do we give you? We spoke early on of the actual application, transport, and media layers, combination of the 7 layers of the ISO. Our radio module typically applies or includes the bottom 2 layers. And this would allow you to communicate via UART to our host and our module. So in your host, you would typically put in the application information or software, and our module would include everything downwards. Right, which is an actual physical layer, the radio stack, including the protocol. One more point here to point out, certifications required to use the frequency spectrum. Our modules using this frequency all have CE certification, as well as FCC if required, and also ARIB or ARIB for Japanese market, and other specifications or certifications are possible as well on demand. Most of the rest of the world actually comply to either the European or American standards. I'm going to leave that there. Let's have a look at the next slide. We have, with all our radio modules, the UART interface, and I'll put in some pictures here of our older modules. But all in all, we could support you with 20 years of experience in radio hardware and radio stack design. And maybe our expert here, Matthias, could maybe give some comments on the actual content of the stack. Mind you, I'll ask him a few questions later on, because I'll see he's been answering the questions on a chat forum here. So don't hesitate, place your questions and he'll answer them one by one. Right, the simple UART protocol to control the radio module, which is the data transmission, control, and configuration. What do I actually need? If I want to include and implement a radio module, I need to design this into my system. And I put in 2 slides here of one of our latest modules, the Tarbus 3. Most important, you'll see, is the actual VCC and ground. Connect those, but the antenna and 2 lines to input data, the UART input, which is the TX and RX lines, and that is about the minimum we need. Have a look at the specifications of all these modules. In this case here, there are some a nicety here which we have. If you look closely, a lot of small components on the actual board integrated into the module. We have 2 varieties. You could either use the PCB antenna integrated into the module, or you could apply an external antenna via the pad as seen here. So you have 2 options depending on what your implementation is. You'll see on the left-hand side, the antenna is option VCC and ground, reset and boot. Right, I'm looking at the watch here, time's running. I'm close to the summary. What else do we have? We spoke of the software earlier on. Dig or search for a wireless connectivity SDK, the software development kit. And here we have something very interesting. The drivers in C source code for all SRD modules, as well as USB sticks of Würth Elektronik eiSos. In other words, here we have implemented the command interface for the modules. You can download this. We also have it running on our little Amber Pi. I'll show that shortly. But what you can do is take the C source code and integrate it into your actual host. And with your application and the software development kit, you would be up and running very quickly to communicate via UART to our radio module, and the reverse would happen on the receiving end. As easy as that. One more slide I have here, evaluation kits and the advantages thereof. On the right hand, you'll see we have a typical evaluation board at the top here with our module on there. You could attach a stub antenna here, and you could connect via USB to the module to transmit. A nice option would be our radio module mounted in a USB stick, some pictures of our modules, and in the middle, the nice red picture here, you'll see our Amber Pi, which fits on top of a Raspberry Pi. It has a radio module on 868 megahertz here as well, and you could, within a very short time, read the sensors at the bottom, transmit the data on 868 megahertz, and you could test whatever environment you'd like to implement. Right, the advantage here, obviously, with all these development boards is that you'd have access via pin header to do certain tests and measurements, amongst other also current measurement and power measurement. And you have the option of our software development kit. Have a look in there. The programmers will love to play with this. Ladies and gentlemen, I think this is going to round it up so far, because I've been keeping an eye on my clock here. We have just about completed half an hour here. Maybe one question which I'd like to quickly post here is, what are the advantages of our proprietary protocol versus other protocols? Maybe I'd like to post this question to Matthias. Matthias, what do you see the advantage of our proprietary protocol?
Hello. So it's quite simple. The overheads of the header in a proprietary protocol, it's much smaller than if you have a non-proprietary one. For example, if you have a Bluetooth or a Wi-Fi protocol, there are many data which are sent besides of the payload. And on the proprietary radio, you mainly send addressing data in the header, but the remaining part, it's the payload.
Yes. Okay, interesting. Many of these complex protocols actually have a very big overhead, and we could actually reduce this, or we tend to reduce this. You could, in fact, use different addressing modes, which could also affect the overhead size.
So here's another question. It's about the DSSS feature, the spreading feature for getting higher ranges. The question is, what's the actual improvement of this coding method? And it's to get an estimate, we get around about 6 dB range improvement via this method. It means 6 dB, it's the double of range roundabout.
Yes, I can remember our slide previously. 6 dB gain would be about double the range.
And to continue with another question, also about the DSSS, is this feature available in all our modules, in all your modules? And it's not. This feature is quite new. It's implemented in the chips which came on the market for last year, meaning that the modules of newest generation that we offer, they have it. The modules of second generation, they do not have it up to now. So
okay. I'm checking through the chats. There's one more I'd like to maybe just discuss with you quickly, is the overhead of our proprietary protocol. The header is in fact not very long. I believe it's somewhere, could be around about 10 bytes of data per package. Am I correct there, Matthias?
Yeah, that's right. It depends on the features that are included in the protocol, but usually it's less than 10 bytes per packet, yes.
Okay, and the complete package then could be roughly around about 250, 255 bytes of data, whereby bigger than that, you would then split it up and make smaller packages out of that.
Exactly, yes.
Right. Here's an interesting question as well. Relating to protocol, what is the difference between flooding mesh and routing mesh? One of the questions here. I think I'll pass that to Matthias as well. Flooding and routing, the difference?
Yeah. So if, routing mesh is a mesh network where there's a master node that knows the way from node A to node B if you want to send a message from node A to node B, meaning that this path information has to be part of the protocol. Therefore, the protocol it's somehow bigger than if you just have a routing mesh, because at the routing mesh you just relay a message. Yeah, meaning that if you receive a message and if it's not for you, you just repeat it, and this just needs an TTL byte in the protocol, a time to live byte, and nothing more. No routing information, just a TTL.
Okay, right. The flooding mesh being slightly simpler in that it tends to just flood the system. You reach your destination as well, because all these mesh systems simply have the nice feature of increasing your range and your availability of nodes and masters in a mesh network. Right, what else do we have here? Oh yes, one of the questions always asked in the past as well, and I see here's one more as well from one of our customers or participants. What about the modules and their certifications? Are they all certified for which European markets then? Maybe Matthias, the topic of certification of our modules.
Yes, so our modules are pre-certified for the European market with the CE or the RED, it's radio norm of the CE. Also for FCC, the USA, IC, Canada, and for a few cases also for the Arab, for Japan. Meaning that if you integrate our module in your end device, only for the CE and only for the FCC, the measurement of the unwanted emissions have to be done in the end device. For the IC, Canada, and also for the Arab, the Japanese market, no measurements are needed for your end device. So you can plug the module into your end device and use it.
Okay, Matthias, thank you very much. One question also, which I had a little bit earlier on here, is hardware related. When would you use an external antenna and when do you prefer an internal antenna? Well, there's a lot of antenna theory. I know that in essence, if you want good range, a long range, you'd use an external antenna. For shorter distance within a building, you'd probably use an internal PCB or chip antenna. But at the end of the day, it's a matter of testing, and it's a cost factor as well, because having to design and integrate a complex antenna could be a cost factor. Sometimes it's easier simply to design in a PCB antenna or a chip antenna, whereas external antennas probably are better for range. However, you could also just take a piece of wire. I've unscrambled, taken apart my paper clip here the other day. In fact, it's 9 centimeters long. I cut off a little bit and I got down to 8.3 centimeters. It works equally well. Just by the way, Matthias, anything on antennas you'd like to mention?
Oh, of course. I mean, if you have the space, an external antenna is always better because of its characteristic. In case of internal antennas, meaning for PCBs antennas or chip antennas, because of the size, the characteristic of the antenna, it's somehow limited, because it's not that omnidirectional as you have the characteristic at an external antenna, and meaning that you have to take care how the orientation of your end device is, because the gain in a certain direction, it's better, one in another direction, it's a bit less good, so to say. Therefore, if there is space, use external antenna, because the gain it's better, and therefore also the range.
Yes. Okay, well, it looks like the smaller PCB and so on are more directional. One last comment on my side, in fact, is that avoid mounting the antenna straight or flush onto a housing or anything which could be conductive or ground plane. Antennas like to have some free space around them, so even with the PCB and chip antennas, try to keep them clear from the wall of the housing and so on. There is a lot of theory available in books and on the internet. At this stage, I think we've answered most of the questions. The remaining questions, I think we'll just clarify them via email. At this point, I'm going to leave the chat open for a few more minutes, but in the meantime, I would then like to thank everybody for the participation. Thank you, Matthias, for your help, and for Eleni and everybody in the background for making this webinar possible. From my side, thank you very much. Have a good day, and well, till next time. Good day.